Students, today's lecture is about the IUPAC rules for naming coordination complexes, and the objectives of today's lesson is that you will be able to name the coordination complexes according to these rules. Students, let us start today's lecture by studying the rules which are given by International Union of Pure and Applied Chemistry, and we are going to apply all these rules on some examples for practice. Now the first rule is that as in the simple ionic compounds, cation is named first and after that anion. Now students, look at this example which is a simple ionic compound. It is sodium chloride. Sodium is the cation and chlorine is going to be the anion. So the name is sodium chloride. Cation precedes the anion. Similarly, students, for coordination complexes, we are going to apply the same rule, that we are going to name the cation portion first and after that the anion. Whether the cation is complex or it is simple, we are going to write the cation first and after that anion. For example, in this K4FeCN6, potassium is the cationic part and the coordination sphere over here is the anionic part. So the name is potassium ferrocyanide. Students, the second rule is that while naming the complex ion, irrespective that it is the cation or anion, ligands are named first in alphabetical order. Look at this example. We are seeing that this is the coordination sphere. It comprises of ligands and the metal atom. Now students, we are having three ligands over here. One is amine, the second one is chloro, and the third one is nitro. So while naming, we have to keep in mind the alphabetical order. And we are going to name the ligands first and after that the metal atom is going to be named. Now students, the oxidation state of metal atom follows after we are going to write its name. And it is noted by Roman numerals in parentheses. Now look at this example and the name is going to be tetraamine. Why it is tetraamine? Because we are having a ligand, amine. And how many amines? 4 amines. That is why we have written tetraamine. We are naming amine first because it starts with A. Then chloro as it is starting with C. After that, nitro as it is started with N. So we have to follow the alphabetical order. After naming the ligands in the coordination sphere, we are going to name the metal atom. So we have written over here platinum. And the oxidation state of this metal atom is going to be mentioned in parentheses and we are going to write in Roman numerals. And after we have completed naming the cationic part, then we are going to name the anion, which is a simple ion which is called as sulfate. So students, the name of this coordination complex is tetraamine chloronitro platinum 4 sulfate. The next rule is when a complex has an overall charge, then ion is written after it. Means student, if we are having only the complex ion, then the name is going to be terminated by writing ion. For example, we can see that over here there is a charge on this coordination complex. So students, it is going to be hexaamine cobalt, and then we are going to write its oxidation state, which is going to be 3. And we are going to end the name by writing ion. So the name is hexaamine cobalt 3 ion. Now students, let us study the details of these rules and how we are going to apply them. The first rule is that we have to identify the type of the complex. Now what do we mean by saying type of the complex? The complex may be a cation, simple. It can be an anion. It can be a neutral complex having no charge at all, or it can be a coordination compound comprising of the cation as well as the anion. So in the first example, you can see in hexaamine cobalt, we are having a charge of +3. So this is a complex cation. In the second example, it is tetracyanonickelate and it is having a charge of -2. So it is a complex anion. In the neutral complex, the overall charge is 0. So it is a neutral complex. But in a coordination compound, we are having cation which is going to balance the anionic part. Students, the second rule is for naming of the ligands. As we already know that ligands can be of three types. They can be anionic, they can be cationic, or they can be neutral. So for anionic ligands, names of the anionic ligands are modified to the end in O. For example, if we are having a ligand F negative which is fluoride ion, the name is going to be fluoro. The IDE is going to be replaced by O. So it is going to be fluoro. Similarly for chloride ion, the name is going to be chloro. For bromide, bromo. For iodide ion, it is going to be iodo. For oxygen atom or oxide ion, it is going to be oxo. For cyanide ion, it is going to be cyano. And for carbonate ion, which is a bidentate ligand, it is going to be carbonato. Similarly, students, for hydroxyl ion, the name is going to be hydroxo. For sulfate ions, sulfato. For amide, the name is going to be amido. For nitro group, we are going to see that the name is nitro. For NO3 minus, it is going to be nitrato. For thiocyanide, the name is going to be thiocyanato. And for oxalate ion, it is going to be oxalato. So if we are having anionic ligands, you have seen the ending name is going to be ending on or modified to O. Students, for neutral ligands, the names of the neutral ligands remains unchanged. But over here we are having two exceptions in the names of water and ammonia. The names for NH3, which is ammonia, is going to be amine when we are going to write them as a ligand. Similarly, students, for water, we are going to use the word aqua or aquo. Similarly, for carbon monoxide or carbonyl, CO, we are going to use carbonyl when we are going to use it as a ligand. Similarly, for NO group, we use the name nitrosyl. All of these are examples of neutral ligands. Now students, over here we are having a bidentate ligand which is ethylene diamine. As it is also a neutral ligand, therefore the name remains as such. It is ethylene diamine. When we are going to write it as a ligand, sometimes we do not specify the complete name. We abbreviate it as EN. So these are the examples of neutral ligands. Students, for positively charged ligands, they are end by IUM. For example, in hydrazine, NH2 is hydrazine, but when hydrazine takes up a proton, it gets a positive charge. So it becomes NH2, And if it is going to be used as a ligand, the name is going to be hydrazinium. So the name is ending on IUM, from hydrazine to hydrazinium. Similarly, nitrosonium. If NO is having a positive charge and it is being used as a ligand, we have to write nitrosonium ion as it is a positive ligand. Students, next we are going to discuss the ligand multiplicity rule. The number of ligands present in a complex is indicated with prefixes like di, tri, etc. Or sometimes we use bis, tris, tetrakis, pentakis for organic ligands. So students, if we are having monodentate ligands, then if only one type of a single ligand is present, we do not need to write any prefix. But if we are having two same types of ligands, we use the prefix di, tri for 3 ligands, tetra for same type of 4 ligands, penta for same type of 5 ligands, and hexa for same type of 6 ligands. But students, if we are having polydentate ligands, Bis is the prefix when we are going to have same two polydentate ligands. If you are having same three polydentate ligands, then the prefix that is used is tris. And if we are having same type of four polydentate ligands, the prefix that is going to be added is tetrakis for organic ligands. For example, students, we know a bidentate ligand which is going to be classified as polydentate ligand like ethylene diamine. So if we are having two ethylene diamines, then the prefix that we are going to use is bis. So for two ethylene diamines, we are going to write bis ethylene diamine. Means we are having two ethylene diamine molecules. Students, the next name is for naming the metal atoms. So the rule is if the overall coordination complex is an anion, means it is having a negative charge. The ending name of the metal atom is written as ate. ATE is attached to the metal center. For example, students, look at this example. We are having a coordination complex. Now this is the cationic part, but the coordination sphere, you can see it is anionic because it is written after the cation. So the name is sodium hexanitro. We are going to write hexanitro first because it is the ligand. After that, the metal atom. But since the metal atom is present in the coordination sphere, which is anion, that is why the ending name of this metal is going to be ate. So we are going to write cobaltate instead of cobalt, followed by parenthesis, and within the parenthesis we are going to write the oxidation state of the central metal atom. To show the oxidation state, we use Roman numerals just like 1, 2, 3, 4, 5, etc. Now students, here are some examples of some transition metals, that how we are going to write the name of the central metal atom when it is a part of the coordination sphere, which is anion. So we are going to write ferrate for iron, cuprate for copper, stenate for tin, argentate for silver, plumbate for lead, and cobaltate for cobalt. Students, I hope these rules are clear. Now let us apply all these rules on the metal complexes and practice naming these coordination compounds. Students, the first practice that we are going to do is with the complexes which are going to have anionic coordination sphere. So these are few examples in which you can see that the coordination sphere is carrying a negative charge. Therefore, these are the complexes in which the coordination sphere is negatively charged. So what are the rules that we have to apply? First, we have to write the name of the cation. Since the anionic part is a coordination sphere, so the cation must be a simple ion, as you can see in these examples. After writing the name of the cation, we have to mention the ligands which are going to be present in the coordination sphere. And students, remember that the ligands are named in alphabetical order. After that, we have to mention the name of the central metal atom, which is a transition metal, followed by its oxidation state, which we find out by working out the oxidation states on the coordination complex. So students, here is the first example. We have K3FeCN6. So first we are going to write the name of the cation, which is potassium. Remember students that for simple ions, we need not to write that how many these ions are present. Either it is a cation or anion. For simple ions, we do not mention the number of that ion. Secondly, we are going to name the coordination sphere. So starting with the ligand, we have only one type of ligand, which is Cn, and how many cyanide ligands? 6. So the prefix hexa is going to be used and the name is going to be hexacyano. After that, we have to mention the name of the metal. Now the metal atom is present in the coordination sphere, which is negatively charged. So as the rule we have already discussed, that the name of the metal is going to end on 8. So for iron, we have to use ferrate, followed by its oxidation state. Now the oxidation state of iron in this compound is +3. Why it is +3? Because K positive carries +1 charge and we are having 3. So it is +3. The cation charge must be balanced by the anion charge. So the charge on this coordination sphere have to be -3. We have to work out in the coordination sphere in order to bring about -3. So students, Cn is a monodentate ligand having -1 charge. As we are having 6 Cn ligands, so the total or net negative charge is going to be -3. So iron must possess a charge of +3 in order to bring out -3. -6 plus 3 will give -3, which will be counterbalanced by potassium +3. So the oxidation state of iron in this compound comes out to be +3, which we are going to write in Roman numerals in parentheses. So the name will be written as potassium hexacyanoferrate 3. Now students, let us look at the next example, which is quite similar to the first one, but you can see the change in the number of atoms of potassium. It is K4FeCN6. So we are going to apply the same rules. Write the name of cation first, which is potassium hexacyanoferrate 2. Now students, the oxidation state of iron in this compound is 2. How is it so? We can see that potassium over here are 4 atoms giving a net positive charge of +4. So the charge on the coordination sphere must be -4. And we have to work out the coordination sphere to bring out -4. Since the ligand is going to carry a charge of -6, so iron must be +2 in order to bring out -4. So iron is in +2 oxidation state in this compound. And students, the name of this compound is going to be potassium hexacyanoferrate 2. Another example is sodium hexanitrocobaltate 3. As you can see, sodium is a cation and coordination sphere is the anion. And students, we are having 6 nitro groups, each carrying -1 charge, so net negative charge is -6. In order to bring out -3, the charge or oxidation state of cobalt must be +3. So this -3 will be counterbalanced by 3 sodium atoms giving a total +3 charge. That is why we are going to mention the +3 oxidation state of cobalt as cobaltate 3. The name of this compound is sodium hexanitrocobaltate 3. Another example is sodium tetrahydroxo. Now we are having hydroxyl group. The charge on hydroxyl group is -1. How many hydroxyls we have? 4. So the net negative charge is -4. Since we are having 2 sodium ions, so the net positive charge will be +2. In order to balance this +2, we need -2 on the coordination sphere. How is it possible that this -4 should be summed up with +2 in order to get -2? So -2 will be balanced with +2. And the oxidation state of zinc in this compound is going to be +2, and the name of this compound is sodium tetrahydroxozincate 2. Now students, you have to concentrate on the name of the metal atoms, as all these transition elements are present in a coordination sphere which is negatively charged, so its name is ending on ate, A-T-E. Students, now we are going to practice some complexes which are going to be neutral on the whole. So the first example over here you can see, which contains carbonyl as a ligand. Now students, you know that carbonyl is a neutral ligand, so the oxidation state is going to be 0. Similarly, if the coordination complex is neutral on the whole, it should have a net charge of 0. It is only possible if nickel is also in zero oxidation state. So the name of this complex is going to be tetracarbonyl nickel, and the oxidation state is going to be written in parentheses. Notice, student, the name of the central metal atom is written as such. So the name is tetracarbonyl nickel 0. Second example is, you can see that it is having platinum as a central metal atom, ammonia and chlorine atoms as ligands. So the name is going to be diamine dichloro, because we always write the name of the ligands first in the alphabetical order, as amine starts with A and chloro starts for C. And students, you can also see the use of di as a prefix. As these two ligands are monodentate ligands, that is why we are using di as prefix, because you can see 2 chlorine atoms and 2 amine atoms. Now students, the name of this compound is diamine dichloroplatinum 2. Now how have we obtained this +2 oxidation state? We are having 2 chlorine atoms, each carrying -1 charge, so it is going to be -2 on the whole. Amine over here is a neutral ligand, so overall charge it contributes is 0. In order to balance the coordination sphere to obtain a neutral ligand, it must be +2. +2 and -2 will give a net charge of 0. Therefore, the oxidation state in this coordination sphere of platinum is 2. The name is diamine dichloroplatinum 2. Now students, the next example is triamine trichlorochromium 3. Now students, the overall negative charge which is going to be provided by 3 chloride ions is -3. Ammonia is a neutral ligand. Therefore, in order to balance out -3, the charge on chromium is going to be +3. So the oxidation state of chromium in this complex is 3. The name is triamine trichlorochromium 3. Another example is, students, you can see over here En. En stands for ethylene diamine, which is a bidentate ligand from the classification of polydentate ligands. The name is diamine trichloroethylene diamine cobalt 3. Now students, amine and ethylene diamine are neutral ligands, so the oxidation state is going to be 0. We are having 3 chlorine atoms, a net negative charge of -3. In order to balance -3, we are having a charge of +3 on cobalt. So the oxidation state of cobalt in this complex is going to be 3. The name is triamine trichloroethylene diamine cobalt 3. Students, you have to consider the alphabetical order of the ligands: amine, chloro, and then ethylene diamine. Next students, we are going to practice the names of coordination complexes with cationic coordination sphere. So here are some examples. Let us practice them. The first example is hexaamine cobalt 3 chloride. Now students, how do we name such coordination complexes? We have to write the cation portion first and after that the anion part. We have to write the name of the ligands first from the coordination sphere, then we have to write the name of the metal atom followed by its oxidation state, and after that we have to write the name of the anion, which in this case is going to be the simple ions because our coordination sphere is cationic. So students, over here you can see the coordination sphere. It is going to carry a positive charge. How? We are having amine as ligands. How many? 6. But it is a neutral ligand, so overall charge is going to be 0. We are having chloride ions as anions because it is out of the coordination sphere. So students, the charge contributed by 3 chloride ions is going to be -3. So we need to have a +3 charge on the coordination sphere, and it is only possible if cobalt is carrying a +3 charge. So the oxidation state of cobalt in this transition complex is +3, and the name is hexaamine. As we have to name the ligands first, you can see the prefix hexa because we are having 6 amine molecules. After that, we have to write the name of the metal atom. Now students, we are going to write cobalt as such, as the coordination sphere is cationic, not anionic. If it was anionic, we were to write cobaltate. But since it is a part of positively charged coordination sphere, we are going to write the name of the metal atom as such, followed by the oxidation state, which is +3. After that, the name of the anion. So the name is hexaamine cobalt 3 chloride. Another example is bromo pentaaqua. Aqua is the word we write for water. Students, we do not write water when we use it as a ligand. Instead, the name is going to be aqua. Now students, you can see the overall charges. We are having Br2 as anion, -1 charge on each, so the net charge contributed by anion is going to be -2. It should be counterbalanced by +2 on the coordination sphere. How is it possible? Bromide ion in the coordination sphere carries -1 charge. 5 water molecules contribute 0 charge as it is a neutral ligand. So, in order to obtain +2, the oxidation state of chromium should be +3. +3 and -1 will give +2 on the whole, which will be balanced by -2 of the anion. So students, the name is bromo pentaaqua chromium 3 bromide. Let us look in another example, which is tetraamine copper 2 sulfate. Now students, look at the charges. Sulfate carries a charge of -2. So the charge on the coordination sphere should be +2. How is it possible? If only copper is in +2 oxidation state, because amine is a neutral ligand. So students, over here you can see that the oxidation state of copper in this coordination complex is 2, and the name is tetraamine copper 2 sulfate. Sulfate is a simple ion and it is the anion of this coordination complex. Next example, the name of this is diamine diaqua copper 2 nitrate. Now students, let us work out the oxidation states. Water or aqua and amine are neutral ligands. So the oxidation state of copper is +2 because NO3 carries -1 charge and we are having 2 NO3s. So the net charge contributed by the anion is -2. So the charge on the cationic portion must be +2, and it is only possible if copper is in +2 oxidation state. So the name is diamine diaqua copper 2 nitrate. Now students, let us practice some complexes which are ions. This is the first example in which you can see we are having cyanide as ligands. How many? 4. 4 into -1 will give -4, and as the charge is -2, so zinc must be in +2 oxidation state. -4 and +2 gives -2. So the name is tetracyano, as we have to name the ligands first, after that the metal atom, and then the oxidation state. As it is an ion, so we are going to write ion at the end. So the name is tetracyano zincate. Now students, we are not writing zinc, we are writing zincate. Why? Because this coordination sphere is negatively charged, and when the coordination sphere is negatively charged, the name of the central metal atom ends on ate, ATE. So the name is tetracyanozincate 2-ine. Next example. The name is hexaamine as we are having 6 amine molecules, which is a neutral ligand. So overall charge is 0. And as the coordination sphere is in +3 oxidation state, so the oxidation state of cobalt in this coordination complex is going to be +3. So the name is hexaamine cobalt 3-ine. Now students, you can see that the name of the central metal atom is written as such. Why? Because it is a cationic coordination ine. Next example, it is tetracyanonickelate 2-ine. Again, we are going to write nickelate because the overall charge on the coordination sphere is -2. So it is an anion. We are having 4 cyanide ions, 4 into -1, -4. In order to obtain -2, the oxidation state of nickel should be +2. So it is tetracyanonickelate 2-ine.